Welcome and thank you all for joining us today. So what will you see during this hour? It won't be an introduction into statistics or experimental design. I'm also not going to tell you how to teach, no worries, because you are the teaching experts. My goal today is to inspire you on different levels, how to improve the way you teach statistical thinking to the engineers of tomorrow. There are many factors that can make teaching better. We strongly believe that teaching with the data and learning from data requires the use of software. So tools are definitely one factor. In a minute, I will show you a case demonstrating how to use JUMP so that you can see yourself how intuitive it is. I also have some quick examples to highlight briefly some additional features which we consider to be useful in engineering courses. A second factor is about teaching resources, including demos, exercises, e-learning, and so on. They allow students to help themselves and can make the life of the lecturer or the course developer much easier. With JUMP, you neither need to teach the software nor to worry too much about troubleshooting of user issues. Instead, teach students to learn from the JUMP help, from webinars, e-courses, textbooks, and so on, and show your students how to become lifelong learners. JUMP is really about real-world problem solving and not about dry mechanics or theory. A third factor is, of course, teaching methodology. So keep in mind that JUMP is perfectly suited for active learning, blended learning, or flipped classroom, but I believe this transfer to you. After wrapping up, we will come back to your questions. Do you know that from the first version on, JUMP software has been designed for the use of engineers, scientists, and researchers who need statistical discovery on their desktop? Today, I use JUMP Pro 13, which is included for Windows and Mac in all academic site licenses. Check the JUMP Starter to see which features are JUMP Pro only. So there's also a JUMP Pro summary showing all Pro platforms and specific features. By the way, my window on the left shows a JUMP journal, which is typically used to collect analysis results, but it is also useful as a central element of any presentation or lecture. The next case has been chosen to show how your students would work with data. I suggest to follow my demo from a student's perspective. It's about the questions we ask and what we do to get answers, and maybe some new questions as well. By the way, all data I use today are from the JUMP sample data, 500 data sets, which ship with the software. Okay, so this case is about the tablet manufacturing process. Our continuous response, so this is one column here, together with the categorical version, which is lot acceptance. The continuous response is dissolution. Let me move this up a bit. So the continuous response, we want that this dissolution is higher than 70%. So that means that 70% of tablets or more dissolve in water within an hour. And this is also reflected as a specification limit in a column property. So dissolution has been measured for 90 batches of tablets, along with all process settings like API, particle size, mill time, screen size, blend time, compressor, and so on. So now the questions are there any issues with data quality or with the process itself? Which settings influence dissolution? And can we build a useful model for this manufacturing process? And later on, can we use this model to optimize the process, maybe to find better settings? And after optimization, what about real-world stochastic variation introduced to process settings? How does that influence the defect rates to be expected? So let's start with data quality. So I can use the help if I'm interested in checking outliers. Outliers, I see, oh, here's a platform, explore outliers in the screening menu, and I can call this. I disable all categorical variables, and then I just choose these predictor variables, my continuous predictor variables, to check for outliers. So there are several tools to explore outliers and also to manage them if there are any. So here I can set a tail quantile, maybe 30%, and then I add 2 times the interquartile range to the left and to the right. And then we see that there are a few values outside of that range for certain variables, including force, coating viscosity, and so on. An alternative is I could also look into multivariate outliers, and this gives me a graph showing the Mahalanobis distance. And an option here is maybe to select all the data points above the upper control limit. So these are potential outliers, and I could assign a different marker type, so to mark them as potential outliers for later studies. The same menu, screening, has explore missing values platform as well. So here I take all my variables, basically put them in. I get a warning, continuous only, okay. And then I click OK. And we see we don't have to worry about missing values in this data set. So there are no missing values at all. But here you see that there are several tools for exploring missing values and also for imputation. A great tool for categorical variables is the Recode Utility. So if I start this, here you can check all the values in these categorical variables, and there are no strange values or there's no mapping required right now. But if you have spelling errors, or if you want to group maybe similar values, the Recode can do a great job and be a great time saver for you. Okay, so the next question is, how good is our process? So this is about stability and capability of the process, and dissolution, still our main response variable we are interested in. So let us go to the Analyze menu, and then the Quality and Process submenu has a first command, which is the control chart builder. Now, stability is maybe what we are interested in first, and control charts are typically the way to explore process stability over time. And this is an interactive tool, so I can drag and drop dissolution to Y. I could change a lot of things here, but I just keep the default. I say done, and we see the control chart on the left. We also have the lower specification limit, our 70% here, and we also see this on the histogram. And all the values below are defects, and they are marked in red on the control chart. So we also see that at least the process seems to be stable, but it's not very capable. So here we see that 15%, 15.5% of our data points are below the lower limit, are out of spec. So that's maybe a first interesting indication about the quality of our process. So let us start to look into some relationships now. So first thing, so always recommended, if you start with new data, choose Analyze Distribution for univariate analysis. And here I select all my variables, the two responses, continuous categorical, and all the predictor columns. And I want to look into the distribution of these variables. So on the left, we have dissolution. Because there is a specification limit, also the distribution platform shows us capability analysis right away. And then we have the other variables. And here I can select the rejected batches. And then I see the same data in all other variables highlighted. So now checking rejected. So what do we see? Probably rejecting a batch is related to low mill time and maybe to higher screen size. Checking other variables. So these are all process settings, potential predictors. Maybe here higher spray rate also correlates with rejected batches. That means lower dissolution. As always, so there's not just one predictor explaining everything, of course. So the predictors, the settings also go together, influencing dissolution. But this is a first interesting indication. Another tool recommended to start exploratory analysis with new data. So is the graph builder, first tool on the graph menu. So here we see the interactive palette of the graph builder, and on the left I have all my variables, and now I can drag and drop a certain number of dimensions to the right in order to graph the data and to see relationships or visualize our variables. So we saw that there seems to be a relationship between dissolution and spray rate, right? So that's what we saw on the dissolution output. So I put it in here, and now we see dissolution versus spray rate jump automatically adds a smoother to the picture, and I can change the lambda here to change the smoother. Or I can change it into a simple regression line. So when I'm done, I click done. But first, maybe let me add the coating viscosity. So some maybe system experts suggested, maybe this relationship depends on coating viscosity. Can we check this? I drag this third variable, and maybe I can put it here, or color, or overlay. So this looks interesting. So I remove the confidence intervals for the fit. I disable them, and then I click Done. And now we see that there is an interaction here. So we see that the relationship between dissolution and spray rate is different for low coating viscosity compared to high coating viscosity. So the first case is the higher spray rate, the lower dissolution, and here we have the higher, a different slope. So there's an interaction. So that's also an interesting finding we could use later when we start building a model. The next step could be to look into bivariate relationships. So that's the fit y by x platform. And here I choose dissolution as my y, the response. And we already saw that screen size seems to have an influence on dissolution. So in this case, I have continuous versus categorical. So this will lead us to a one-way ANOVA case. Other cases are continuous. This would give us a scatter plot, and then we can fit models, align, and so on. And also logistic regression or contingency tables, mosaic plots. All these types of analysis can be started from the fit y by x platform. So it's generic. JUMP takes the modeling type of all variables into account to give us the corresponding output, and also to offer all the tools and additional settings on the red triangle, which make sense in this context. So the display options have a jitter settings, which you can enable if this helps to see the data points. And options are, for instance, show us the means and the ANOVA table here. So this ANOVA output tells us the p-value is low, so this is significant. And that means we can reject the hypothesis that there are no differences at all. So there seem to be some differences. Where are they? Between which groups? So for that, I can follow the compare means option, and they maybe can do a pairwise student t test, two-sample test between all pairs between two groups. And you probably know that it's a good idea to correct for multiple comparisons tests, and a better alternative, if you have many comparisons, is probably the QKey honest significant difference test. And what we get from both methods are comparison circles. And the circles already tell us by color if the means between two groups are significantly different or not. If they are different, the colors are different. On the right-hand side, the circles are also bigger because this test has less power than the left one. This is just a short example of, let me close this one. And then multivariate analysis. So this is under multivariate methods, the first platform, multivariate. So this can be used to look into correlations and scatter plots. So here I choose all my variables as y's. I get a warning again, only continuous, please. Okay, and I click OK. So here we have pairwise correlations, the table on the top, and then we have the scatter plot matrix. So maybe let me change. The marker size a bit. I press the command key to do this on all outputs, on all scatter plots at the same time. So this is the broadcasting of commands feature in jump. And the form of the ellipses tells us about the correlation. So maybe you want to shade them, and then if the ellipses get smaller, the correlation gets higher. So there are more options here. So you can also go to principal component analysis and then factor analysis from there. From this platform, I could also add parallel plot, for instance. And then looking at spray rate again, we see that we have a lot of green, so accepted at low spray rate, but we also have a lot of red rejected batches at high spray rate. And rejection high spray rate seems to correspond with higher mill time, but also with, higher blend time, but also with lower mill time. Okay, so final step for exploratory analysis. I already use a model here, and this is from predictive modeling partition. And partition can build different types of trees. So here I use a standard decision tree using the categorical response, not acceptance. And I want to explain this response by our predictors. And Trump will pick the best predictor to split the data into green and red ones as much as possible. So I can do a first split and another one to grow the tree. And here we see that screen size has the most power on the first split. And it's very green if you look at screen size 4 or 3, and it's very red if you have screen size 5. For screen size 4 and 3, if the spray rate is below 404, then it's all green. So this path here could be maybe the first change request to your process to avoid screen size 5 and higher spray rates. Okay, so this was a first model, but for exploratory purposes. So now I want to go on and build a model which I want to use for optimization and simulation later. And building models in JUMP, so there's a generic platform again called Fit Model. You can find on the Analyze menu. And I choose the solution as my Y to model. And then for model effects, I only pick the hot axis. So the predictors where we've already found some significant influence on the solution. And these are mill time and screen size, coating viscosity, and spray rate. Only 4 of our predictors, but I add some more complex model terms using this response surface macro. So now we also have quadratic terms like mill time and two-way interactions. So this could be probably better used for optimization at the end, assuming that the screening of our variables was already done. So let's see if we get a useful model here. So I run the model, and this is the report. So the first graph on top is the actual by predicted plot. So this looks reasonable, and we also see some metrics. So the R square is 72%, what's not too bad. And we also get a ranking of our model effects sorted by p-value. So lowest p-value, highest significance on top. And again, the winner is screen size. And then interesting, so on the second place is a quadratic effect of mill time in this case. We also see that some effects are not significant at all, so I can select them and remove them interactively from our model. And all outputs are updated automatically, and we see the R² just dropped by 2%, but the model is much smaller. Okay, let me collapse some sections. So you also get a diagnostic output, of course, to check modeling assumptions. We have the scaled estimates here. On parameter estimates, so here we have the estimated parameters, and I can also right-click to change this table. For instance, if you are concerned about multicollinearity, I could add the variance inflation factor for these parameter estimates, and so there's nothing to worry too much about in this case. Now, the effect tests output shows me all the effects, again with significance. So here I can also right-click, and I can maybe sort this table by p-value. So we see screen size on top, and then the other effects with decreasing significance. Okay, so how does the model work internally? So we can have a look at the prediction expression, the internal formula. If you want to see the formula, yes, you can see it. But I hide it again right away. So maybe more interesting than visualizing the formula is saving a formula, or another option here, if you just want to deploy this model, you can also publish the prediction formula. This gets you to the formula depot. And here you see that you can generate C code, Python code, and other type of code from your model for deployment on other systems. If you want to stay in JUMP, so go to Save Columns, and then you can save the prediction formula. You can save a lot of other information, of course, but saving the prediction formula creates another column, a new column in your data table. And here you see again a plus sign. If you click, it's the same formula which is shown in the formula editor. So you can add new rows, and then this column would predict and calculate the response based on that formula. But maybe more interesting than reading formulas is definitely to visualize the model and have an interactive tool to ask, what if? What if the coating viscosity goes up? So down here on the profiler, we have all our settings for the 4 variables we have in our model. And then we see the influence on our response, which is dissolution. So here you can see if the coating viscosity goes up, dissolution goes up. And you also see the confidence interval. But changing coating viscosity, look to the right, spray rate. So this is the interaction we saw earlier in the graph builder. So that the influence of spray rate on dissolution depends on another setting, which is coating viscosity. So here for higher coating viscosity, so it's almost flat. It's still quadratic, but it has not such a strong effect. But for lower coating viscosity, so spray rate has a very strong decreasing effect. So you can see the influences. You can also see interactions. And now our goal is to maximize dissolution. So how can we optimize the process that we get the highest dissolution as possible? You can start to find this optimal point, operational point manually, but you can also ask JUMP by adding the desirability formulas. This tells us the higher the better. What is our specification in this case? And with this, we can ask JUMP, find the best settings for us. Best in this case means getting us the highest dissolution as possible. And the best one is 80%. And we also see that the confidence interval is not below 70%. So this already looks good and quite useful. If you want to export this, maybe before doing this, let me say, okay, this is an interesting point, and let us remember these settings, give it a name, and now we have this best operation condition saved here in the profiler. So to save this, to export this, so what I could do, take the selection tool by pressing S or from the tools menu, and then I can select this section from my report, and now I could press Ctrl J, and this would add the result to my journal. Ctrl J is really a very convenient shortcut to add any interesting findings to your journal. Another option is, if you want to present this report, this output to others and decision makers, maybe management or system engineers, you can export this maybe as interactive HTML. And then I click Next and save this as an HTML file on my desktop. And now this is open in a browser. So this is not JUMP anymore. So this is interactive HTML, HTML5. And the nice thing is this is still interactive. It maintains a lot of interactivity you also have in an interactive JUMP report. Okay, so are we done? Not yet. So what about defect rates under real-world conditions? So for that, there's also a simulator using Monte Carlo simulation built into the profiler. So here I could add stochastic variation to our settings in different ways. So I just add random normal distributions of noise here. I can also add some noise to our output, maybe caused by the measurement system. And then I can click simulate. And in this case, JUMP simulates 5,000 data points, taking the stochastic, the random variation into account, and it shows us the defect rate to be expected. So it's less than 1%. Remember, we started with 15.5% at the beginning. And 5,000 simulated data points each time I click on simulate. And the defects are also shown below our specification limit. So it is this tail of this histogram for dissolution. I would like to close the case with 2 comments. So first, many sample data sets come with stored scripts. So here you see a lot of scripts in the top left table panel. So you can just click the green triangle to run them. Click the green triangle, and this is the output from another slightly different analysis. But you can also save any analysis when you're done. Go to the top red triangle and then save this analysis as a script to the data table or to the journal. And if you save it to the data table, it will be added to your table. The language use is called a JSL, jump scripting language. And this is the language and the interface which is also used to develop custom applications. You can build custom applications and also integrate with R or MATLAB, for instance. So the second comment, JUMP can build many different models, including neural networks, random forest, and so on. So the model comparison platform helps to find the most useful model or to build meta models, maybe being better than any individual model you created. An important concept in predictive modeling is, of course, cross-validation to ensure that you model the signal and not the noise in your data. So splitting the data for validation, I go again to the help, validation, anything there? Yes, make validation column. So this is very convenient in JUMP Pro. This utility helps you to create subsets for training, validation, and test in different ways using formulas or fixed assignment or stratified or other ways. Okay, so that's all about the case, and now I have some more short examples to show you other use cases of JUMP we consider interesting in engineering courses. On top, and I think it's a good idea to have this on top, is about statistically designed experiments. So here we have another sample data set, and if you open them, you see the sample data. Of course, here we have 3 continuous columns, and we have 1 continuous response, and the experiment is already done, so the response column has the values and the measurements already filled in. So this is a typical design table created by the JUMP DOE tool. And there are many different DOE tools in JUMP, including all the classical designs, but also more modern screening designs like definitive screening, and the most versatile and flexible way to get an optimal design, which is the custom designer. With any design, you also get scripts. So from here, take a sample data set with a design, and then you can go back and check the DOE dialog. And here you see how this design was created. It's a response surface design, a box design in this case. And the first question the design tool asks you is, what do we want? And you can specify a goal. In this case, the goal is to match a target, and to optimize the settings to match a target for scratch. And before creating the design table, you can also evaluate the design. You have the power analysis. So here we see the power, so the probability to detect an effect if the effect is really active. And you see that the power is quite low compared to main effects for a quadratic effect. But if you know that this effect size is maybe twice as the size of other effects, so I can add this, and then we see the better power in this case. So the power analysis, then you can also look at the prediction variance in your design space, and you get a variance surface after a second. It's a bit slower, caused by the ongoing recording on my computer, but this is the surface, and we see that the variance goes up in the corners of our design space. And you can also look at aliasing and color maps on correlation to get a better understanding how good the design is before you make the design table. So this is to go back, and you can also go forward, because a design table also has an analysis script added to the table. So as soon as your experiment is done, let me close this guy. So as soon as your experiment is done, you can just click the model script, and you get a fit model platform pre-configured for you. So according to your specification of the assumed model during the design phase, this is the corresponding analysis step, and you can just run it from there, and you see again a profile output here showing you how this works. And this was about match the target. So here I could ask maximize desirability, and then you see that we are matching the target of 450. So it's also shown here. Now, so for this, you can also look at the distribution output. Here we see our factors again, and by clicking, you can see that this is a balanced design. So here we have the center points in the middle, the center values of our factor settings. So this is also helpful to explore design and understand it better. And if you want to learn more about DOE, so go to jump.com academic, or directly to jump.com academic/teach, and there you have all the resources for teaching and learning with JUMP. So I also have it here. And the course material library shows you course material for different types of courses. So there's one for engineering quality reliability, and also a lot of resources, including webinars, and also other resources to learn about design of experiments using JUMP. So this really deserves more time we don't have today, but it's definitely a leading and major application area of JUMP as well. So the second example is more about statistics and some basics. So here we have another design table, and we are interested in tensile strengths measured in this sample data set. So I open the distribution platform, and here we see the distribution output. Let me show this horizontally. Maybe it's easier or more convenient for you. And what we get down here is the 95% confidence interval for the mean. And on the red triangle, you can also change the confidence here, so from 95% maybe to 90%, and then we see for a 90% confidence interval, we also see the mean, but also the standard deviation, and there are two intervals with lower and upper order. But there are also other intervals probably interesting in teaching engineering courses. So there are tolerance intervals as well, and also prediction intervals. So a prediction interval, for instance, could specify or could give you an interval for any number of future samples. So if we get 10 more samples, so what is the interval that where we find these new samples at a confidence of 95%? in this case. And this is the result here. So this is the output. So we have 95% confidence and the intervals. Sorry, the prediction interval down here. And so hypothesis testing can be also found on the red triangle. So you probably saw this in other webinars. So testing for the mean, just choose this command, and then I can set a hypothesized mean. I could also add a standard deviation and do a z-test. I can also do a non-parametric test at the same time. So they typically go together, parametric and non-parametric, and jump, and then you get the output here. And we see that it's a very low p-value, so we can reject this hypothesized mean. And here you see where it is, and you see the sampling distribution for the mean. If this would be the true mean, and this is the observed mean, the red line. There are also animation tools to teach the concept of p-values in an interactive way, so they are also typically very, very useful. If you want to skip all the theory about hypothesis testing and inference and so on, you could also use bootstrapping. You find in Jump Pro. It's a bit hidden, I have to say, but a right-click on a statistic gives you a simulate option, which is about randomization testing. So this also combines the column switcher to switch a formula column to reshuffle a column, or you can bootstrap. So if we bootstrap the mean in this case, so I choose bootstrap, or maybe choose 500 bootstrap samples to save some time, and then the bootstrapping starts. And when this is done, you get a table with bootstrap samples, and this table has a distribution script which can be run. And here we see for the mean on the left, we see the confidence intervals down here from the bootstrapping. So this is very useful as well to get empirical intervals quite easily on many different types of statistics. Okay, so let me close that one and then briefly mention some other examples. So nonlinear seems to be an interesting platform in engineering courses. So this can be used for curve fitting, for instance. So if you go to specialized modeling and you can fit a curve, so we have a y and an x in this data set. And now what is a good function here? Maybe quadratic, maybe another one. So logistic parameters. Oh, this looks much better, the blue one. Yeah, and you can add more functions, and this model comparison tells us if there is the correct function in this set of models, which is the best one. Yeah, and this tells us that the logistic 2P does the much better job in this case. So there's also another platform called nonlinear. So again, I set the response. And if I have static values in x in here, then I could choose a function from a model library, from built-in functions. I could also explore them visually to see how they work and what the parameters do. So this is a library with built-in functions, or I choose a custom formula. So here we have a column with a formula, and we see the formula down here. We have two parameters, a B0 and a B1, and we see the starting values. And now I can click OK, and then go and ask JUMP to solve this problem and to optimize these two parameters. So the good news here is this problem converged, and these are the two parameters. So it's maybe 1 and 0.05. So this is about nonlinear relationships. Measurement systems analysis, also quite important, and this can be found under quality and process, measurement system analysis. So here we measure a Y in this data set on these parts. So these are our samples, and we have several operators, and they use several instruments. I keep all the default settings here. So the default for the method is EMP, evaluating the measurement process from Wheeler. And here we get a graphical output. I cannot go into details right here, but there are many other visual outputs, for instance, telling you about interactions. And then we see that there seems to be an interaction with instruments. And from here, we also can look at the results, and we can look at the variance components. And here we see that there seems to be an issue with repeatability. So a lot of the variance, 32%, is coming from repeatability problems. But reproducibility is better. And the variation we want to measure, we want to see clearly, is just around 34%. And all of them sum up to 100% total variation. So measurement system analysis can be made very easy and very visual as well, directly telling you the quality of your measurement systems, the process, and so on. So this is another example about quality and process. So here we have semiconductor data, and we have many processes, a huge number of processes. And you can look into process capability, and this platform gives you a goal plot. So you see which processes have a very high variability, high standard deviation, and which ones have a lower variability, but really shift on their mean to the left or right. And you can set the PPK, and then all processes in the red zone are below the PPK you set here. Oops, 1. And you also see a capability box plot to see how the individual processes are doing. For hundreds of thousands of processes, you can look at characteristics. But if you're interested in how they are doing overall, so there's also a nice overview beside shift detection and so on, an overview called process performance. And here we see the green area is where we want to be. So that means this is a stable process and a capable process. So there's nothing unstable in this data set, but these are the ones maybe not fulfilling the specification, the requirements. So they are not capable. So I can look at them and quickly look at the graphs for these processes, or quickly look at some control charts for these processes. And here you see directly what's going on, what's going wrong in these cases. And finally, an interesting topic, reliability and survival. And if you want to teach this as well, you have everything built into JUMP on the reliability and survival menu. So let me open the last sample data set I want to use today. And here we have censored data, and I use the live distribution platform to check the time to event and to fit models, fit distributions to these data. So the question is, when will it break? And here we look at microprocessor data. So when will it fail? And the censoring information goes in here, time to event. And we have count data. So I put this in as frequency counts and then click OK. And here I can start to fit a distribution. I can also change the scale. In this case, all the points should follow a straight line. And this is the probability plot, a quite common graph you look at in reliability studies. And on the right, again, we have an interactive profiler. So here we can see that after 2,000 hours, maybe we can expect that 2% of our microprocessors will have failed. So this is predicted using a Weibull distribution. That's the model in this case. And don't forget, so the data is quite complicated in this case because we have a lot of censoring different cases, which can also be better understood maybe by looking at the event plot. So this is right censored, for instance, so we don't know when after that time. And we also have these here interval censored. So the failure was between 1,000 and 2,000 hours, but we don't know exactly when. So this is quite complicated. And that really closes the last of my examples. So I already showed you in the browser where to go for resources. And resources are, of course, important. They can also make a difference teaching better, especially in engineering courses, because there are a lot of resources available. And the best place to look at, and I just refer you to our portal, this place is jump.com/teach. And then you get to the portal, and there you can look at e-learning courses, one-page guides from the learning library, or also interactive tools. Books are also listed here, and you already have a good choice of excellent books for engineering courses. Here are just some of them. And one other book has been selected to share with you as a free copy. And this is probably your next step. So this is mentioned down here. And I have to summarize now. So my summary is the software can make a difference. It can make teaching better if the software is an enabler in teaching and not a barrier. And that's what JUMP tries to be. Okay, so we have to close at this point. We're really appreciating your feedback. If you have feedback or other suggestions how to use software, how to make teaching in engineering better, please let us know. We would appreciate any discussion with you.